architected and commercialized NEC's own AI-driven security platform. And this is absolutely my favorite part because I'm not sure how many of you have patents, but I think it's amazing that he does not have one patent. He has filed 48 US patents. And with that, Albert Lee.
Okay, thank you for introduction. Let me get my slides ready.
Oh, Albert, one more thing before I let you go. We will be doing Q&A at the end, so please do send me messages in the chat with your questions, and we'll allow for 15 minutes of Q&A when he's finished.
Okay, thank you, Mike. I believe all you guys can see my screen, right? So, hi, this is Albert. I'm the Chief Scientist at Stellar Cyber. It's my great honor to get invited to talk to such selected audience. As Mike introduced, I'm both a security guy and a machine learning guy for many years. I started with security, and then I had been working on machine learning for years and apply machine learning to solve security problems. So in this talk, I would like to talk about demystify how machine learning is used in cybersecurity. Moreover, I will talk about how to connect the dots through graph machine learning to reconstruct the attack big picture from weak signals for more sophisticated attacks. The AI technology has become a main driver for technology innovation, right? There's many companies across different fields apply AI technology to their product. This is from the CB Insight, right? They rank the AI 100, right? The 100 startups is active in applying AI technology, and they do it every year. So AI technology has become a driver across different fields to move the world forward and make a big impact. Since the booming of AI, so does the hypes. So for the general audience, sometimes it's hard to know and understand where are we now and where are we heading to. According to some survey, right, there's a quite number of people, including tech people, are somewhat pessimistic about the future, right? And I'm not sure how many of you guys watched Terminator movie series before, right? That's a good kind of movie series. I like it. In the movie, there's the Skynet, right? The ultimate AI machine, right? Get self-conscious, then rebellion from the human control and rule the world. Some people actually believe such a thing will happen in future. Like for example, the Elon Musk, right? Who publicly speak about his fear about the artificial general intelligence. In his remark, he mentioned the robots maybe one day become the super being. They are faster than human, they are smarter than human. We just cannot simply catch up. And also in another interview, he says he's scared of Google. He says that Google is the AI company that is somewhat dangerous, and will the Google become the inventor for Skynet? It's a debatable topic because it's about the future. The future is always hard to predict. The different tech leaders have different view. Like for example, there's a debate between the Elon Musk and Mark Zuckerberg, the CEO from Facebook. The quote from Elon said, I have talked to Mark about this. His understanding on this subject is limited. The response from Mark is that people who drum up doomsday scenario, I actually think is pretty irresponsible. Not only them, the Googler like Eric Schmidt also joined the conversation, right? Then he also mentioned he thinks Elon Musk is exactly wrong. Exactly wrong. So in some sense, for the future, probably it's very hard to know what's going to happen because its future is hard to predict. When the general intelligence will come, we don't know. But at least we know it's not there yet. Then probably more important, we need to know where we are and the history. Then think about, for now, how do we leverage on AI to move the world forward for security and other like a field, right? In order to understand where are we now, right? Then we need to be a little bit more scientific to define the concept. Right? I have been seeing people use a lot of different concepts like AI, machine learning, deep learning interchangeably, but actually they are different levels of concept. The artificial intelligence, AI, have the biggest scope, right? The machine learning actually is a subfield of AI, which is more about data-driven techniques. Through data, you can train model and predict things and detect things, right? And the artificial intelligence have other sub-branches, for example, expert system, which is more about leverage on logic inference type of system to make it intelligent. And for the machine learning, which is data-driven, the deep learning is just a subfield, which is more about leverage on deep neural network, which is a hot baby now, but it's just a subfield, right? Because of the big data, leverage on the deep model from the deep neural network has made a great success, but it's just part of the camp of the machine learning, right? So I just first want to get the concept right. The second, I would like to take a brief look of the history of AI, right? Future is hard to predict, but we can learn something from history. The artificial intelligence literally started in 1955. In the Dartmouth conference, the people coined, some researchers actually coined the term AI, artificial intelligence. Actually, even just a few years before that, the Turing, right, the computer scientist, and also the great mathematician, right, who has kind of already invented the Turing test, right, try to separate machine from human, right? And when AI is born, many years it progresses slowly, right? In 1960s, like people invented the first chatbot. Then there's some AI winter in between that until 1980s, the expert system, the logical inference-based system is kind of booming and also made the commercial applications such as expert system. Then after that, around 1990, is the rising of machine learning. The machine learning is rising is based on a couple of facts. The first is we have the faster and faster machines. Second, with faster machines, we collect more and more data. Then it's make it available to leverage on data-oriented approach. Right. Then the machine learning also take a long incubation until we recently see more and more big applications in the commercial world. And in the 1997, right, the IBM Deep Blue leveraged on a supercomputer to win the chess game against the world champion for chess. That one actually still is the older generation of AI technology. It's kind of a brute search type of technology leverage on like alpha beta pruning. And then there's this 2002, right? Some like a little like a Roomba, right? Which is iRobot company. This robot cleaner, right? Made it to many people's home, right? Then until the recent like 10 years starts from the 2009, right? There's more and more AI applications, and also that then we enter the age of the deep learning, right? The deep neural network standing out. In 2009, the Google started their self-driving unit, and then later on become Waymo now. Then 2011, the IBM Watson, right? Winning the Jeopardy, right? The question answer game. And almost in the same year, Apple released the Siri. And then actually it's about another startup, they release Siri. And then the Google Now, and then the Amazon Echo 2014, right? Those type of question answer machines right now is a kind of benefit everyone. And in 2016, DeepMind, a subsidiary from Google, released AlphaGo, right? And have the game with Korean master of Go, right? And win the game. And it shows like, because Go is a game with a very huge space. It cannot do in the exhaustive search way, right? So then they showed with the deep reinforced learning, and they can win the game, right? That is a kind of big deal. And also there's a lot of hype regarding machine is already outpaced human and so on. And then let's look at the progression of AI in security, right? In the early days, like in the 1987, the Stanford Research Institute actually have a project called the IDES, Intrusion Detection Expert System. It's a very early stage of IDS, and even from that name, it's already AI, right? So in some sense, they leverage on the hot topic of expert system in the 80s, right? They create this project. And in the 1998, right, the DARPA launched a project, released some public evaluation data set for IDS evaluation, right? That has become a standard data set used by many machine learning researchers to benchmark algorithms. So for security, actually, until recently, like in recent 10 years, we see more and more product is claim they have the machine learning built in, right? So machine learning in security product is only kind of widely used in recent 10 years. So that's a brief history. So next few slides, I'm going to talk about supervised learning and adaptive learning, which are commonly used in security detection, right? So the word supervised, if you think about this word, it gives you some idea about the supervisor or teacher, right? Which means someone want to teach you or convey knowledge to you, right? Provide knowledge. Then provide knowledge in what form? Actually, for the supervised learning, the algorithm takes the knowledge in the form of class labels, right? In some sense, for supervised learning, the human need to prepare data, which with labels, and use the labels to teach the machine, right? Just like if you want to teach your kids what is banana and apples, right? You give a lot of samples for banana and a lot of samples for apple. Finally, he gets the concept. This is banana and apples. Similarly, right? In the picture I show is more like for security, right? It's more supervised learning sometimes used for classify malware. Then we also give labels for the malwares. We give a label, right? The positive label, right? And then for the goodware, we can give a negative label and so on, right? And usually from supervised learning, it needs a training phase, or you can say a learning phase. Usually it's offline, right? Usually require large amounts of data, the malicious samples and the good samples. The goal for the training is to learn a classifier or a machine learning model. The machine learning model is somehow a model. It represents those samples in some feature space and try to find the optimal decision boundaries to see which part is good, which part is bad. With training, right? Then the machine learning model usually can, the supervised learning model usually can do the online inference. Given an unlabeled sample, right? Suppose somehow you get a new malware, it's unknown, yeah. Then you want to classify it good or bad, right? Then give this model, right? What it does is somehow for this sample, it calculates some features, and then maps this sample into the feature space, and then to know whether it's good or bad, right? Then later on, it can return with high probability, maybe this sample have this label, right? That's a brief introduction for supervised learning. Then with supervised learning, right? we can solve certain problems in security. Supervised learning is used to deal with the cases. We can easily label the bad guys, right? Because supervised learning usually require you have different class of data, right? And also the different class is best to be like balanced. By that I mean, for example, you have 1,000 bad samples, you have 1,000 good samples. Right? You don't want to have only 2 bad samples, 1,000,000 good samples. That is not a balance. That sometimes does not work out. That require you somewhat easy, because good sample like a normal traffic and normal data is relatively easy to collect. The harder part is you need to get enough bad samples for the training, right? That is managed easy to do in malware classification, spam filtering, phishing, malicious domain detection, such as DGA detection for detect the domain generation algorithm used by botnet and so on, right? So down to the question, when we can use supervised learning, supervised learning is for the case we can easily get the labeled samples. Supervised learning is actually very important. For example, the Andrew NG, right? A Stanford professor, a big name in the deep learning and the machine learning, when he gave a keynote at NIPS, which is a top AI conference, he mentioned the supervised learning is holy grail for machine learning, right? Which means if you could apply supervised learning, you should do, because usually it's more mature and also give you better accuracy. So that's supervised learning. So next, I'm going to unbox the supervised learning a little bit, right? This is probably the only slide I'm going to talk on math a little bit. But the take-home message also pretty simple, right? So that's the I think I should not lose your guess. So for the data, essentially is a bunch of sample, right? For example, just like say you want to classify some fruits, right? Then you want to first make it become math problem by find some features as a vector, essentially a set of features. For the first type of classification, the feature I can think of is, for example, size, color, shape, right? Then with that, then essentially you want to have a model function, which is given every instance, right? For example, you have a banana. It's yellow, it's curvy shape, it's maybe 3-inch long. Then you want to map that with a feature through some function to the label, right? For example, banana, right? That is ideally you want to find a very good function so that you give all these like fruits, it can perfectly match to their class. And then people usually use the parameterized model functions. The reason is because there's a lot of different choice we can make on F. It gives different accuracy. Just take a one-dimensional case, right? You just have one-dimensional feature you want to predict Y, right? Then you could have different, for this just says linear model. A different linear model, you have different parameters to do the job, right? Some is better than others to do the prediction or to do the classification. Then with that setup, we could turn the supervised learning problem to an optimization problem, right? So in some sense, with that setup, we can define a cost function like a JW, right? Then to measure for different choice of parameters, what is the average cost of prediction error on a data set? And then we can leverage the machine learning problem. We turn the machine learning problem to find the best W that minimize the JW function, right? That is more like a turn the machine learning kind of problem to a more standard optimization problem so that we can solve mathematically. And usually people, like for most machine learning problems, we use gradient descent, right, to solve the optimization. The gradient descent is about if you have a function G, right, with certain shape, then you want to find the gradient, essentially a slope, right? Just move some steps along the slope and reevaluate again, right? Then keep moving until you reach the minimum, right? So that is a standard way to solve the optimization problem. So the take-home message for this slide is supervised learning and also many machine learning problems Finally, we turn to optimization problem to solve. In order to solve the optimization problem, we need to define the cost function and the features and so on, right? So in some sense, it's a optimization. It needs the human to define the goals. So at least this type of technique usually is very hard for general intelligence. So then next, I'm going to talk about unsupervised learning. When we say unsupervised, right? Think about this word. It gives you an impression, independence, right? Independent thinker, scientist. Somehow those guys are smart. They can discover knowledge. Then they discover knowledge in what form, right? Unsupervised learning essentially discover knowledge in data patterns. Let's take the fruit example, right? Assume there's an alien come to Earth, right? They never knows the apple, banana, this type of thing, right? But at least when he look at a group of objects, it can find a set of objects, yellow curvy shape, another is a red round shape. They are different clusters, right? That is more like the clustering algorithm, right? So in terms of type of unsupervised learning used in security, there are many, but here I just list two, right? Commonly used. One is clustering, another is anomaly detection. The clustering is try to learn the similarity. You want to put the things similar to a class. The anomaly detection is try to learn dissimilarity. Essentially, you want to learn something different. It turns out anomaly detection make quite a big deal in security because we want to detect something different, like attacks. So let's look at anomaly detection in more detail for a moment. Anomaly detection is try to detect large deviation from usual case. In some sense, in order to detect something's unusual anomaly outlier, we need to understand what's usual. Then we need to model the baseline, we need to model what is usual, right? There's different ways to model usual. For example, we can compare with our own histories, like time series analysis. Like assume like this is a home, right? It has the power consumption for different hours. Then we can measure it for days and weeks, even months. Then we can learn the pattern. Then we can learn there's a daily pattern. And then, for example, now we can predict roughly, usually how much electricity you should use. But if it turns out your actual usage is much, much more, then we know some anomaly happened, right? That's from time series. Then we also can compare with the peers. For example, we can compare with similar homes, right? Whether it's an apartment, townhouse, house, and so on, right? Then the data can come as a group, but some is outliers, seems weird position. Then we know it's different, it's outlier. And sometimes even more complex. The objects are all normal, but the relationship are not, right? So then we want to learn what is your relationship among the object and try to flag out what is unusual relationship with graph analysis. So this is anomaly detection, right? Anomaly detection has been used for security, right? Anomaly detection also have its limitation. Anomaly detection is good to detect anything unusual. But on the other hand, for security, we want to detect secure instance. Actually, there's a huge gap in between. Fundamentally, right, so anomaly detection just report you anything unusual. Could be anything, not necessarily attack, not necessarily secure instance. So beyond the secure instance, there's a lot of other case of anomalies such as nuance, noise, other type of problems. Now the question is, how do we filter them out to make it more suitable for security? The key is to design the security anomaly detections. Just like in the previous slide, we talked about knowledge, right? The designer needed to know security and embed security knowledge into design so that the detection is better suitable for security, not something else, right? For example, for doctors, they probably can use anomaly detection, but they probably should embed different knowledge, right? This is a try to see for anomaly detection, in order to make it really work with security product. We need security people, not only machine learning people. And we need know both. So some people say mathematicians can do anomaly detection, can work for security. That's not exactly true. It needs a more security background. Then another thing can help is adaptive learning, right? Sometimes it's easy to confuse this with supervised learning. They have some similarity, but different. The supervised learning usually require a large amount of samples, thousands or even millions of samples, and also require balanced samples in different classes, which means you need to have millions of malicious samples. On the other hand, anomaly detection, you only need to train on the normal data. It's a little bit easier to apply. But the anomaly detection sometimes have higher like noise and so on. Then is there anything in between we can leverage on, right? That is the question we want to answer. For that is adaptive learning. The adaptive learning usually is started with anomaly detection, right? Some security analyst is using the AI algorithm with anomaly detection, and once it sees the result, it can give some feedback, right? Then the algorithm can take the feedback to learn the preference from the analyst and utilize that to reduce false positive, right? And usually for such scheme, even a small amount of feedback, like 10 or 100, already benefit a lot, right? Can dramatically improve the accuracy. This is similar to the search, right? The years before when we use Google search, it's kind of everyone get a similar search result. But today, if you do Google search, your result will be different from mine because the Google already personalized, right? It try to learn your preference and get the best result for you, right? For security, actually, even a very limited small amount of feedback is very useful to guide the machine learning algorithm such as anomaly delay detection, right? Because anomaly delay detection, if without embedding any security knowledge, it just report anything unusual. Even with security knowledge embedding, sometimes it does not learn this environment so well. Then any hint give to it can help to improve the accuracy. So next few slides, I'm going to talk about why some machine learning algorithm can get superior result, right? What is things we need to take off in order to get the best result? In order to answer this question, we need to look at 2 dimensions, right? First is data. The data is very important. You have to give the right data to solve the right problem. For example, if we want to find someone with high blood pressure, it's best just to measure the blood pressure, right? If we only measure temperature, it's very hard to use that data to, no matter how accurate it is, the data is, to solve that problem, like detect some blood pressure or some blood problems. Similarly, for machine learning, right? Once you have a goal, you have to have the right data. Even you have the right data, it still have the second part. You need to choose the right model. The right model is just like the boat fit with nuts, right? So somehow they should have a tight fit. The machine learning model needed to capture the intrinsic nature of the data in order to get the best result. It's not like blindly throw a model through some data, you can get the best result. For example, the secret sauce behind the success of image or face recognition, right? Recently, the image and face recognition made a tremendous improvement, right? There's the Stanford ImageNet project, right? To benchmark large-scale image classification job for different algorithms. And right now, the accuracy machine already can beat the human. So the secret weapon is, in some sense, is because for the image, right, it have a nature of this locality. I'm going to illustrate that. And then people invented the convolution neural network. It's very good to capture such data locality and make a huge difference. This is the standard image, right? For the image evaluation task called Lana. And then For example, if you only want to detect some feature like eye, right? You only look at this sub picture is enough. Forget about this whole picture, you can recognize eyes, which means the data have locality, the pixel around it is most important to detect something in this region. The other region, not too much big deal. With that, then people invented the convolution idea, right? In some sense, it's just have a filter function or like this shaded like area. For every pixel, you just calculate something for the pixel around, right? Is enough. You don't have to use faraway pixel into the calculation. With that, then right now, right, what we can achieve is given a picture, right, with raw pixels, right? Then people can use multi-layer of convolution and some other layers to make an end-to-end image classification to recognize this is a car, right? So years before, usually computer vision guys needed to craft features, for example, some type of feature for this part of the car, like a mirror. But today, they only need to use convolution, right, to fit this block to map to some unit here, and gradually the magic happens. Then we can achieve human level, the image classification accuracy, which is amazing. So another case, the secret sauce behind the success is the voice recognition. So for the voice, right, it's more like a sequential data. When you speak, actually, you speak along the time a wave, right? This wave can be translated mathematically as a vector of numerical values, like along with time. And this data is sequential data is perfectly can be fit into the recurrent neural network, which is a neural network structure. It can capture the early kind of the input, can influence the prediction result for later input, right? Like assume we want to do some words recognition, right? If I say a little bit harder sentence, like I say the sea, the first C is a verb, the second C is ocean. Without to know the position, without to know the context, it's very hard you can recognize that sound, that word. That require the neural network be able to memorize the context and use the memory to improve the accuracy, right? So that also get a very amazing result for recently, like all this Amazon Echo, like Siri, like Google Home, and so on. So next, I'm going to talk about some new trend, right? And also my personal opinion, right? There's a potential secret sauce for large range of security problems is to learn the object relationships as a graph. So for security, a lot of problems is more care about interaction between the different objects. For example, Alice, using her email client and send a attachment to the Exchange server, and then further send to of her colleague. And one of the colleague, Bob, click the attachment, download it, and then it kind of the Outlook fire up the Excel reader file and present Bob. Unfortunately, this document is a weaponized document. It also started PowerShell sneakily and doing something bad. And another of her colleague, Charlie, didn't open the attachment, then nothing happens. I just illustrated with some simple graph, right? With node and edges, I can express pretty complex attack scenarios. So for a lot of security things, we can encode it as a graph, the security activities. And then we could leverage on the recent progress for the graph ML, the graph learning techniques to help better understand what's going on and better for detection. The object relationship is very important for models, the security activities, right? Then those relationships can be further expressed as graph. The graph ML is a secret sauce to somehow connect those behavior together so that we no longer learning the individual behavior, but learning the big picture to understand what's going on. That is turned out to be very important for security. For example, right, for the sophisticated attacks, right, it has been kind of target of enterprise. One of the major threat is data breach. The sophisticated attack has been used to target enterprise to leak data and to do other damage. Today, we are in the AI age, right? A lot of business are surrounding data. They need to collect the data and they need to derive intelligence from the data through machine learning AI technologies for their business. Data has become a very critical asset. And also data means customer trust, because customer work with you, trust you can host their data, not breach their data. The data breach really hurt the business. This is a visualization from the Information is Beautiful, right? It visualizes the world's largest data breaches from different years, right? In some sense, every CISO, they want to keep their organization off this chart, right? So it's not so glory to be on this chart. For example, Equifax, right? It have big data leakage, then even cause the CEO step down. In some sense, a lot of what sophisticated attacks is behind the scenes for the data breaches and so on. And also for those sophisticated attacks, it have very long develop time inside the enterprise. For example, according to the FireEye M-Trend report, right? You know, a lot in year 2019, the develop time they measured around 60 days. And if attacks not found by themselves but third party, usually already been there for 100 days. So it's quite hard to detect and early prevention the sophisticated threats, like APT and other type of sophisticated threats. One of the problem is it's not like we lack of the reporting, right? Lack of signals. Today we have the alert fatigue, right? The secret analyst get tons of signals. It's just too much for him even to handle that. And also the worst part is just the wolf coming, right? Then when the real wolf comes, your brain get trained to just ignore it, right? Then in some sense that is bad for security. Then how do we really solve the problem is how we have to better detect such more sophisticated cases, right? So here I illustrate a more sophisticated attack from the target data breach. And this attack is based on many security researchers reverse engineering. It may not be perfectly accurate, but at least largely can represent what's going on. So first, in the target breach, there's some like phishing going on and also try to infect people's machine with botnet. But that is a large scale, probably not targeted yet. And then those phishing email and also infection get to HVAC vendor used by target. And later on, the attacker found this vendor have access to the target internal vendor billing website, right? Then they somehow kind of stolen the credential and be able to log into the target internal website. And then they become starting point for target attack. They explored the internal web app, then installed a web shell. And from there, they immediately did the internal reconnaissance, right? They try to figure out through Active Directory for database because they're shooting for data. Then later on, unfortunately, somehow some machine owned by attacker, the sysadmin log into that machine, right? Then they leverage on the pass hash, like a mimikatz, this type of thing to get the dump of the admin like a hash, right? And leverage on that, they create a new admin account, best one user, right? And also they choose this name is because some commercial software will install, when you install the software, it will also create such a username. And then they did more internal reconnaissance and did lateral movement to target for the database. And then they found the SQL server, they did the database dump and did exfiltration. It turned out it leaked a lot of PII data, right? The personal information, personal identification information. But the attacker a little bit disappointed because they more shoot for credit card, which have more black market value. And then they changed their attack plan to install a malware called the Black POS to the POS machine in target through a compromised software updating server. In some sense, they first compromised this software updating server because they already have root. So for them, it's more about to try to figure out where the server located. Then they found this server, then they kind of push the update with the malware and to infect all the POS machines. Then when you swipe the card, the malware try to read the memory and get your credit card number. And once the different POS machine get the credit card number, the attacker let the POS machine to aggregate the credit number through Windows file sharing to an internal server. And then organize the data there and exfiltrate through FTP to Russia. So if you look at those steps, right, like even partial of them, immediately the CISO or like the senior security analyst will recognize this is a very dangerous threat, has to be stopped immediately. But the key challenge is in day-to-day, right? If you look at individual steps, it's not significant enough. There's tons of other alerts look similar for the individual steps, right? So like many of them. The only makes this thing standing out is the context matters. Somehow we need to reconstruct the strong signals through the weak signals so that we can know what is really going on. That's the power of connecting the dots. To better simplify it and also illustrate, so we use even simpler examples, the bank robbery preparation, right? Like assume someone want to rob the bank, right? Then he did some preparation and he kind of first buy a gun, then a ski mask, then get a very detailed map for the bank and also visit the bank multiple times, somewhat rehearsal. For this type of case, if you look at the individual steps, it's legit. If you look at them in isolation, right? You just try to detect some anomaly on it. It could lead to very high false positive. Like for example, to buy a ski mask in summer is somewhat suspicious, but there's still many reasons can lead to it. For example, I found a good deal, I want to save for winter, right? Or I just want to kind of ski in a cold place. Or just COVID-19, right? I just want to get a mask. Like on and on, there are many good reasons. Probably if you give this problem, you think hard, probably you finally may reach here, the bank robbery. It's not that obvious. But if you look at it from the context, right? Because I tried this, I talked to many people, I gave this context, then they immediately recognize this is possibly a bank robbery, right? Some people buy a gun, right? And some people also get a ski mask and get a detailed bank map and visit the bank multiple times. With more this connecting the dots and link the evidence together to build a context. Within this context, it's much easier to identify this guy is more suspicious than others. As I already mentioned and illustrate, right? If we model the security activities in a graph like this, it's easy to kind of capture the context in the graph. Then is the key, how do we learn something abnormal on it and figure out the big picture? So next I'm going to talk about how we connect the dots through the graph machine learning techniques. I would like to start with a classic example, right? The more like a little bit old school stuff first, then gradually talk about the new things. So in some sense, to propagate influence is important. For example, for security, right? We have the this is a classic method like a Tinder analysis, right? The information flow analysis. Like assuming you have a web app, right? Somehow through the web form, the username is input by user, right? It's untrusted input. But somehow it kind of propagate inside the program, like the program may be presented as a graph, as CFG, right? The control flow graph. Then to the SQL, right? Then the SQL get executed. Then there's a high chance this path can lead to the SQL injection. That is a propagation on color or labels, right? There's also other example like a PageRank, right? PageRank leads to the Google's early success in their search, right? So I was when I was using Google many years ago, I immediately dumped all the other search engine, right? Because somehow at that time, the PageRank can give very good result, right? To make the search result indeed better. The PageRank is an influence-based algorithm, right? Like try to see which one is a big influencer, right? And towards others. And also the more modernized technique, right? For example, we can do the deep work, random walk type of thing on a graph, and then to encode the graph with some data structure for learning. And that also lead to a second topic, right? The graph embedding, right? In some sense, graph is a discrete data structure. Machine learning inherently, it usually works better in a continuous space. So there's a lot of different techniques, right? Try to somehow convert the graph to a vector space, and also during the conversion, also try to reduce the dimensions, right? Because graph is a very high dimensional space. There are so many nodes are different, so many edges. You can think like every edge, every node is belong to somewhat different dimensions. Then with this type of embedding, right, then it can convert to a lower dimension, and also you become points in the embedding space, right? That is easier to leverage on conventional machine learning algorithm to deal with graph. And then there are even research try to make this more natively, right? The graph neural network. The graph neural network is to say the input is graph, and also the neural network structure is made from the graph. One idea is the graph convolution, right? You have this target node, right? Then you have neighbors and neighbors. For example, A have neighbors. Then I can organize a neuron so that the information is from the neighbor's neighbor to this node, right? This type of idea is kind of in recent 5 years. There's a lot of development for the graph ML, and those techniques will kind of contribute to the connect the dots and make the world better. So compare with traditional approach, right? In some sense, when we say connect the dots, we let the machine learning measure the correlation, right? Correlation has been a technique used for many years in security. The new thing is just how do we do better machine learning on top of correlation in a larger scale. In the traditional approach, for example, SIMS, right? The security information, even the management system, we can do alert correlation, right? That usually set up a rule, right? Two type of data you want to set up, or three type of data you want to set a rule, right? The rule is a manual. It's not very scalable. So like if you have 100 type of data, then you think about all the possible rules you can write. It's very large, actually. It's quadratic or even more, right? So, and also it's bounded by the perfect domain knowledge. It's less ubiquitous, right? So it's very hard. You just use correlation rule to do all the data. And the EDR, right? The endpoint detect response, right? Usually endpoint detect response leverage on the process have inherent relationship like a tree structure, right? Then they can do some correlation on the tree, right? And also each process have the user, host, context, and so on. They can do limited correlation, right? It's just if somehow we have the ways to do even more broader scope correlation with machine learning, then we probably can better construct the big picture. So in summary, in this talk, I introduced the machine learning in security. I also illustrate a few cases why the proper machine learning model can become a secret sauce. And I also discussed a little bit on why connecting dots is important for sophisticated attack, and showed how the graph machine learning techniques might help to connect the dots. With that, I would like to conclude my talk. Right, the core message is the context matters. In order to build, detect the sophisticated attacks, we need to build a strong signal from weak signals by connecting the dots through the graph machine learning. Thanks for listening. That's the conclusion for my talk.
Fantastic. Albert, thank you so much for that. That was really a great presentation and has given a lot of us a lot to think about. There's a lot of questions. I'm going to kick it off with my favorite first question, because the ISSA is about many things, but all of us are very much into ongoing learning. And I wondered if you could share with us, do you have a favorite book on AI or ML? If we're looking to expand our knowledge, what would be a good first book to pick up and read?
I actually do not read books for machine learning, because machine learning is a field, the progression is very fast. So the book usually is slightly more classic. So for machine learning, I think there's a lot of good online courses, like it's with visual illustration, a little bit more easier to understand, right? For example, there's the online course from Andrew NG, right? The Stanford professor on the class, on some Stanford website. I forget exactly which one, but there's the open free courses you can take a look, right? There's a video for different sessions. If you only need to care about the supervised learning, then you only need to look at that session, right?
Cool, thank you. And I had
it's a course area, yeah.
I had one more quick question, because all of us are absolutely inundated with vendors that claim AI and ML. Everybody says, oh, we are AI. We are the AI cybersecurity solution. We are AI. And what I want to know is, do you have a divining rod or a specific series of questions that you would ask vendors who claim AI to see, is it real? Is it not real? Do they have deep learning? Are they real? What would you say the best questions to ask if a vendor approaches you and claims AI to see if they're actually real?
Yes, so in some sense, right, because in some sense right now it's quite cheap to claim you have AI, right? You have a little bit something, you can claim you have AI, right? Even you have a Ruby system, some people just claim they have AI, right? So then at least probably the first question is like, what type of AI you have, right? Is machine learning or non-machine learning based? Then top down, right? So if it's machine learning based, then which type of machine learning you are used for solve which type of problems, right? For example, if the vendor says I'm using supervised learning, right? Then for supervised learning, you use supervised learning to solve what problem? Malware classification or some problem, right? Then with that, then you can further drill down, right? For example, if it's malware classification, then at least you can ask what type of method you use. Is deep learning, or is it a simple method? There's a lot of different tools can be used, right? So to me, is the devil in the detail, right? At least need to go to a certain detail level to know how they use machine learning, right? For example, if they say they do like an anomaly detection, right? Then in that case, how do you make sure your anomaly detected is secure instance, right? Then what type of care you take for the model to make sure it's better for security, right?
Great, thank you. I have a question from Lynn Kaiser, and this question is, are simulations or artificial attacks